let me refresh everybody with my talk, and it's my great pleasure to make this very, I would say, very unusual online form to give this presentation. And I'm Yifu Cai from USDC, the University of Science and Technology of China. And today I'm going to share with you some kind of my understanding about the bouncing cosmology, and the title is looking for non-singular bounce, and we expect it to be healthy, especially in this year. We all, and I mean, I wish everybody to be keep healthy in this year. Okay, so to begin with, I mean, every story has a kind of old starting point. For example, for bounce cosmology, I mean, before that we have made a lot of achievements in the particle cosmology, say inflationary cosmology, and this is I mean, here this slide just show a very quick sketch description how inflation could work with. Like we can insert a free massive scalar field and then put it inside a FRW background. Then once if this the field amplitude of the scalar field phi is above Planck, then within that area we have this slow roll period, which can drive acceleration at a high-end scale. And this used to be employed to address a couple of conceptual issues existing in the traditional small Big Bang. And in particular, this inflationary cosmology made a couple of successes, like it can explain the formation of the larger scale structure by virtue of the seed from the primordial fluctuations. And it predicted the nearly scale invariant path spectrum of the primordial density perturbations. And so far, we confirm for most of the inflation models, say the single field slow roll inflation cosmology, the primordial non-Gaussianity, its amplitude is relatively small. And it follows the so-called consistency relation for the primordial gravitational waves, so that the primordial tensor mode amplitude is also small and sizable. But in the meanwhile, inflationary cosmology itself is effective field point of view about to address the early universe, right? So within this theoretical paradigm, we know there are a couple of issues like Transplanckian problem, and it didn't address the initial Big Bang singularity because the geodesic line is not completed in the past, right? It has there's a endpoint at the very beginning. So that means that there exists the initial Big Bang singularity over there. So in order to address these conceptual issues, then later on, I mean, this is the outline of my talk. So I'm going to give first I'll give you a very brief review on bounce cosmology, and then I'll talk about how to make some kind of the systematic model building of the bounce cosmology. And based on these models, we can talk about the cosmological perturbation theory, and then we can arrive at the theoretical and the observational constraints on various bounce models. So following what I talked about previously, and after the after we realize a couple of the conceptual issues existing in the inflationary cosmology, then there's some sort of the alternative proposals. And among them, there is a very representative one that is the so-called exotic cosmology that was proposed almost 30 years, no, 20 years ago. 20 years ago, yeah. And this scenario described cyclic collision of two membranes in high dimension, and if one reduces this scenario into back to a 4 dimension, then there is such a effective field theory description, and that is a scalar field minimally coupled to Einstein gravity. And following the potential of this, based on this effective field theory description, one can track the cosmic phases. I mean, along within each circle, like in this scenario, there is the gigantic domination, and then it turns from it evolves to deceleration and turn around to the contraction. And this contraction happens when the potential evolves to a negatively valued regime, and it becomes very steep, so that it can drive the so-called asymptotic contraction with the effective equation state to be much larger than 1, and then it will arrive at the crunch and bounce to the Big Bang expansion. However, within this scenario, for the 4-dimensional effective field theory description, this bounce phase actually is the contracting phase minimally attached to the expanding phase. So this bounce point is a singular bounce point. And there were a lot of the discussions how the perturbation and the background can evolve through this singular bounce. And then in the literature, there are many other non-singular proposals. Like here, I'm pretty sure there should be much more than the scenarios shown in this slide, but I just pick up several cosmological scenarios that I'm more familiar with, like the pre-Big Bang cosmology, the string gas cosmology, and matter bounce cosmology, loop quantum cosmology based on the quantum structure with space-time, and the mirror cosmology is based on the non-conventional framework. And also there are some bounce models driven by like a ghost field, like a DWIC standard model. And also there are proposals on the new abstract cosmology by replacing the singular bounce by the non-singular bounce. And also there are in recent years there are the Galilean genesis proposals. So there are many proposals, but then we can look at what kind of the challenges that we might have for non-singular bounce cosmology. So I'm going to talk about the theoretical challenge, the challenges from two levels, the background level and the perturbation level. For the background, once when we address it, the cosmological dynamics, the dynamics of a universe, one key parameter is the so-called the equational state parameter. And this equational state parameter can be defined from the, either from the matter components or the geometry side. And for example, if we take it from the geometry side, then this W can be effectively defined as -1 minus 2 h dot over 3 h squared. And in order to realize a bounce, very naively, we can imagine the universe start with a contraction. And this contraction requires h to be smaller than 0, to be negative, right? And typically, once we require this system is well defined, like satisfying the null-entity condition, then in this phase, W has to be has to be larger than -1, right? And after the bounce, if we expect the universe can connect with can transit to the regular thermal expansion, then h will evolve from less than 0 to larger than 0, so from negative to positive, but still at the in the regular expansion, then W still keeps larger than -1, right? So then we match them together, and then we easily can tell at the bounce point, h of course is 0, and in order to make the bounce to be proceeding smoothly, then h dot is larger than 0. So this is the one lesson that we can just very quickly learn from the background equation state evolution. And then we come back to the Fredholm equation. Regarding the Fredholm equation, even let's say naively, the whole cosmological whole background remains roughly FRW background. Then we can write down this effective equation, the Fredholm equation, as the following. So the right-hand side is in terms of the cosmological constant, the curvature term, and the regular matter radiation, and we have the anisotropic stress, right? Also, we have if we have some dynamical scalar field, then we have the additional contribution from this scalar field. And regarding the expanding phase, it is always fine if we keep the anisotropy over there, because it dilutes with proportion to A2-6, right? But if we consider a universe to be contracting, then this anisotropy will be much easily to become dominant over, because it's growing, proportional to a to the minus 6. So that means in order to make the anisotropy to be under control, then we would expect the aquatic phase to be remain over there. So that means an aquatic matter is required by setting its effective equation state to be much larger than unity. And for the non-singular bounds, at the bounce point, h is around 0 and h dot is positive. So then if we insert this relation back to the definition of a W at the very beginning, this first formula, then we can see around the bounce point, it typically expect W to be less than -1. So this means around the bounce point, there should be a duration of the non-end condition violation over there. And yeah, so here I just illustrated by saying, okay, we can consider some kind of the quantum bounce that is realized in terms of the ghost field. And okay, so well, it is possible for the non-energy condition to be violated, but if we only consider a canonical scalar field, then this easily leads to the quantum instability, right? For example, then there's a possible way that we can, namely, we can set the non-energy condition violation only spontaneously happens in the, for example, the infrared regime, such as the ghost condensate, and that can help to yield a non-scalar bounce. Like, for example, just like the new explorative model that was worked out more than 10 years ago. But then soon later, there was a quite famous paper by Steinhardt and Xubingtan. So they point out for this type of the model, if we only consider a passive like scalar field model to drive the bounce, then there's an argument that they made whenever you dilute the anisotropy in the contracting phase, and after that you have to let the connected term x, the value of x, evolve back to the infrared regime so that you can trigger the occurrence of the non condition violation. And then between these two events to be happened, then the anisotropy that you dilute in your contracting phase would grow back right before the bounce. So that so this means this anisotropy issue is widely exist in many non-singular bounce cosmology. So we have to figure out a way that to make sure while we can insert some dynamic phase to depress or to make the anisotropy to be under control, and we cannot let them to evolve back before the bounce. So this is one observation that we have to keep in mind when we do the model building in the theoretical aspect. And another issue challenge comes from the perturbation. That is to say, actually, earlier motivated by the dark energy study, like the quantum dark energy, we realized for four-dimensional FRW universe described by either a single perfect fluid or a single scalar pattern scalar field, and if this matter components minimally coupled to the instant gravity, then there is always a gradient instability if we let the equation state parameter to cross over -1. Naively speaking, so by looking at the single perfect fluid, then you can write down the sound speed square immediately, and this parameter become divergent for the single perfect fluid. This parameter becomes divergent when W reach at the -1, because this factor 1 plus W appears in the denominator. And for the single scalar field, one also can write down the general dispersion, the general form for the dispersion relation as the following: that's omega square equal to 6 square k square minus z double prime over z. And in this case, when W cross -1, the parameter z will reach 0. So I mean, this is a very simple calculation, and everybody can immediately do it even right now. And you can see it's it also becomes divergent for this dispersion relation. So this is actually the lesson that we learned from the challenges for non-singular bounds cosmology. So how we can towards a non-singular bound, and especially by virtue of a single scalar field, to make the model to be as compact, as simple as possible, right? So this was a question that my colleagues and I raised a couple of years ago, almost 8 years ago, and the story arrives at as following. So at that time, I don't want to waste my friends' time to review what has happened about Galilean or Hondevsky, whatever. So today we know that at that moment there was a new theory appeared that was regarded as the most general form of the single scalar Lagrangian yielding the second order field equation. Of course, by requiring the diffeomorphism invariance, and then for this kind of the Lagrangian is written down as the following. And then we observe this Lagrangian we can insert a couple of operators inside. For one thing, previously we mentioned, for example, the lesson that we can learn from the new Epcot model is that ghost condensate indeed can trigger a non-scalar bounds, because that can yield a short duration of non condition. But we need to make it happen spontaneously, and but instead of infinite, but at a higher scale. So then we write down we keep the ghost condensate form, but we let the sign in front of x to be controlled by inserting the scalar field itself. And then from the perturbation level, we know for this type of model, for cases-like model, it cannot realize W cross -1, because that perturbation will become would suffer from the gradient instability. So a simple way to remove this gradient instability is to insert the Hondevsky operator. That is the G as a function of phi and x, and for simplicity, we can see the G only as a function of x. So, and at that moment, we neglect L4 and L5 because these two operators are higher order terms. But for the later study, we actually realized for L4 and L5 that those operators could be important to help the perturbations to evolve through the bounds in a more smooth way. Okay, so then we insert this model back to the FRW background, and then we can write down the expressions for the energy density and the pressure in terms of the following two equations. And then we can derive the general Gaussian equation. And in particular, this P coefficient actually also help to determine this model is free from the ghost issue. Once if the coefficient P is always positive, then there's no ghost throughout the whole evolution. And also, we want to keep the approximate phase, and in particular, we want to accommodate the approximate phase with the ghost condensate phase. So then we consider to take the potential and the G factor as a following. It's two exponential, look like a Gaussian function. And when the scalar field evolving so you can see the scalar field in this plot, it evolves from the negative infinity to positive infinity. And when scalar field evolves along the potential which are within the negatively valued regime, so it can automatically drive the approximate phase. And at that moment, the value of G is smaller than 1, so that means the kinetic term is still dominated by the canonical term. But when phi evolves to some value, let's say around 0, then the value.
There is a question from Michał Artemovsky.
Yes, please.
A very quick question. I'm just wondering, have you reconstructed the potential from the assumption that the field has such a solution?
Okay. So you are saying the solution for phi evolving
given
by the left hand side, right?
Yeah.
So when we do this, actually we consider try to make the semi-analytical solution. So indeed, the potential, the form of the potential is exactly following what we wanted to.
Okay, so it's reconstructed potential, kind of. Okay. Thank you.
So this is a model constructed out of ghost condensate, Galilean, and aporetic phase, right?
Right, exactly, yeah.
So it's kind of egg bonds, EGG egg bonds, aporetic ghost condensate egg bonds.
Well, thank you for making this comment. Yeah. Okay, so then, well, this is one example to illustrate at that moment that a non-scalar bounce indeed can be achieved by a single scalar field, and this model is free from the ghost model, and it can accommodate the dark phase and the ghost condensate phase. And also, we, well, for one thing, yes, the potential and the G factor, it was chosen by reconstruction. So then we still made the numerical calculation to and let the model parameter to be selected for free, so that we can numerically verify that our semi-analytical analysis are reliable. So that was these three are the numerical results, and you can see H. First plot is the evolution of H evolves from negative value to positive value, and the W at the contracting phase obviously is much larger than 1. So that means a dark phase remains until the bouncing phase happens. So there's no worry for the growing back of the anisotropy. So that is that verifies what we have argued. And also later on, we add the we consider the particular Bianchi metric look like this way, so that they involve the anisotropy. And then we found for this type of model, if at the very beginning, if the anisotropy is under control, then this won't evolve back, and the bouncing phase is went through very smoothly. So that verified our argument. Okay, so here's several comments. One thing is that non-scalar bounds indeed can be realized by single scalar field under the help of both the ghost condensate and the Horn-density operators. And the second point is the comment is the primordial anisotropy diluted in the aporetic contracting phase will not grow back. And in this regard, the PKL instability can be resolved for this type of bounce cosmology. But then again, the question follows: is it really stable against ghost and the gradient instability? So far, it looks like it looks good, right? And also the second question that we easily raise is it able to provide us the primordial path spectrum that can satisfy the observations, right? So these two questions are then pointing the study to the perturbation analysis. So then we go to the perturbation theory for non-scalar bounds in foreign. Again, we would like to make an analog to inflation, because inflation indeed is a very successful paradigm for describing the very early universe. And for inflation, that we can learn is that all of the fluctuations emerge inside the Hubble radius, right? And so that we can set up the initial condition as a quantum fluctuation. That means the fluctuation originates from the sub-Hubble scale. And along with the exponential stress, the wavelength of the physical wavelength of these perturbations easily evolve to the super-Hubble scale. And then it can automatically provide a decoherence from the quantum fluctuation to the classical perturbation, right? So this is the basic picture of the perturbation theory for inflationary paradigm. And then from the right panel, we show how the one Fourier mode evolves within the bouncing cosmology. So that bouncing cosmology assumes at the very beginning the universe could be sufficiently large, and so that all of the perturbations emerge still from the extremely flat space-time. And along with the contraction, if we look at the co-moving Hubble radius, then this co-moving Hubble radius is shrinking, and then it can automatically let these quantum fluctuations which emerge from the sufficiently flat space-time to superscale. So that can also provide a decoherent mechanism for the perturbations evolving from the quantum fluctuation to the classical perturbations. And if the bouncing phase going through sufficiently short and smooth, then this duration is expected not to affect the all of the observational range of the perturbation. So this is we can even learn from this sketch plot, even we are not touching any particular theoretical models. So let's see then how we can solve this perturbation evolution for some by taking particular examples of the bounce model. Let's say, okay, it's easy to set up the perturbation. We can let the scalar field evolve in the perturbed scalar field, and we introduce the perturbed metric perturbations, and then one either can write down the equation of motion for the perturbation in terms of gravitational potential or co-moving curvature perturbation or body potential, depending on your taste. And then you can evolve you can solve the perturbation equation phase by phase, from the contracting phase to the bouncing phase, and then evolving to the expanding phase, and match them at each the phase transition point. And also we previously particularly considered a realization of the meta-aporetic bounce. That is because for the meta contraction, it is good to set up the initial condition for all of the fluctuations, and that was a lesson that we can learn from the meta bounce. That is actually the curvature perturbation can form the pulse spectrum, which is scale invariant. And the reason why we combine the meta contraction and the and then which is after the meta contraction, the universe will evolve to aporetic contraction, is because we want the growth of the anisotropy to be under control. So this is the simple argument that we expect. And then for this type of model, we actually solve the curvature perturbation evolving as the following. So in the contracting phase, this zeta goes like this form, and this A is can be regarded as the amplitude, and there's a k dependence on the denominator, and xk describes normalized perturbation mode along with the time evolution. So this factor actually grows up in the contracting phase. And after the bounce, when the universe evolves to the expanding phase, we can see this k dependence can be remained. That means after the bounce, curvature perturbation will become constant again and remain scale invariant. So this example just illustrates that curvature perturbation is no longer a conserved quantity in the contracting universe, and it can transfer from the contracting phase to the expanding phase smoothly. And here is the example. You can see from the left panel that the perturbation, well, here I set t equal to 0 and eta equal to 0. Both two are the bounce point, and you can see the amplitude of potential. The amplitude of the gravitational potential is growing up in the contracting phase and become constant. So that verifies our previous analytical analysis. But for this type of model, even go back to the paper we wrote back to 2012, we realized at the bounce point, the sum speed square actually can be expressed as the following. It's a c square at the moment of bounce, so it's a CSP square. It's roughly equal to 1/3 minus 2 over 3 blah blah blah, and this value actually is exactly almost minus 1/3. So that means at the bounce point, this sum speed square for the curvature perturbation is negatively valued. So this indicates gradient instability. Well, at that moment, we argue if the duration is short enough, then actually this effect on the perturbations are quite controllable. But that again indicates that the model that under discussion is merely effective description, which cannot which is not fundamental enough. And so this is the lesson that we learned from this particular model that we worked on. So later on, there are many discussions about the potential pathologies that could exist for non-singular bounds. There are several constraints like ghost instability, gradient instability, and we don't expect a superluminality. And in general, we can write down the projective action for both scalar perturbation and tensor perturbation as a following. And then in order to make make sure this one model is free from the ghost instability, then that requires the coefficients of GS and GT cannot be less than 0, right? And also in order to avoid the gradient instability, then while the GS and GT are positive, we also require Fs and Ft to be positive, because the sound speed square is defined as C square is defined as Fs over GS. Sorry, my mistake. And Ct square equal to Ft over Gt. So yeah, so this is a mistake I made here. And also, we don't like these values to be larger than unity. Otherwise, it may bring the potential danger of superluminality, right? So then, also there were a lot of discussions upon the mode with the small k value, evolving through the bounds for negatively valued sound speed square. And typically it shows that these modes keep almost unchanged for small k. But for large k, the growth will become very much uncontrollable. So that is the danger issue. And then eventually it arrives at the so-called theoretical no-go theorem. And
excuse me, there is a question by Chun-san.
Yes. I think how to. Yeah, please.
Okay. Why do you think the superluminality is a problem?
This is a good question. Yeah, I know your point. I'm not saying this is how to say. Okay. What I mentioned is that if C square and Ct square to become larger than unity for sufficient long time, then this model will bring some superluminality propagation for the information. However, indeed, for the scalar field, in general, field theory, if this just happened for a very short moment, and if we can make sure the propagation of the information, which follows the group speed, to be still less than unity, then actually that is okay. But then there's sort of the fine tuning over there.
Are you talking about some causality violation or?
Yes, yeah, I'm talking about the causality violation.
Let's look at for example, let's look at this gravitational sector, and if the speed of gravitational wave is greater than unity, and then the causality is just defined by this gravitational cone instead of light cone, I don't see any problem at all.
I think you are raising a very interesting question, but we can discuss later. What do you think?
Okay.
Yeah. Mm-hmm. Okay. So then later on there are some. I have this. There's a very nice work by Yun-Song Piao's group, and the first author Cai is not me. It's a very good friend of me. And then there are also the work by Criminelli, and they point out in order to evade this theoretical no-go theorem, then we can look at the issue from the point of view of the effective field theory. And then we can, by putting off the diffeomorphism invariance at the moment, then we can see what kind of operators can be introduced so that they can evade this theoretical no-go theorem. So by writing down the effective field theory description as the following, then we can immediately see this kind of a theory. Let's say, for example, if we introduce some operators to like the Hondesky or I mean the Horava-Lifshitz gravity, so that can help to make the perturbation to be stabilized. And also there are some particular operators that can be introduced to cure the gradient instability that actually exactly modifies the dispersion relation over the perturbation. For example, the delta K, delta G00, and the three-dimensional Ricci scalar times delta G00. So a conjecture is as following. So if we look for a healthy version of non-singular bounds that still obey the diffeomorphism invariance, then these operators are expected to be included. So, and oops, I made the, that's great. So I actually prepared 3 slides in the following, but then obviously there's a version mistake on this computer and that computer, so I have to show you this 3 empty slide. So, but anyway, so then following this conjecture, then later on, my colleagues and I myself, we worked on the very recently this DHOST, the degenerate higher order derivative scalar tensor theory, which is again regarded as the most general scalar tensor theory, which remains a second order differential equations. Well, it's very embarrassing. And then we found this operator, this theory can include these operators, and then we used this theory to construct the bounce model, and that was a very recent work that I finished just a couple of 2 or 3 months ago. At that moment, that was the most dangerous moment in China. But then it's really embarrassing. There's the version mismatch from the computer. So then, unfortunately, I didn't put it over here in this PowerPoint. Okay, then let's come back to a little bit to the matter-at-rest bounds. So for in general, the quantum vacuum fluctuation affects the Hubble radius in the matter contraction that indeed can generate scale invariant power spectrum. That's why we keep the matter contracting phase. And then for this kind of the period, it can generate non-Gaussianity, which is of order 1. So this can be consistent with observational bound. But when the perturbation evolves to the super scale, the curvature perturbation initially in the matter contraction is going up, but it can become constant in the abstract contraction. So that explains how the abstract contracting phase can make the anisotropic stress to be under control. And also, in order to spread the tensor to scalar ratio, usually one expects the curvature perturbation to be enhanced during the bounce. And the question is it possible or it is allowed? So then, but later on, there's a work by Gaussian, Patrick Pitt, and Lilly. So they point out if we have the growth of the curvature perturbation during the bouncing phase, then there might be a risk to produce a larger non-Gaussianity. So actually, these 2 works are very good works. And then we examined the cosmological perturbations evolving through the bounds very carefully. And we can first we can see the single scalar field, and that originally based on the Hondesky model. And then in this case, the growth of the up on the curvature perturbation can be expressed as a time integral from the pre-bounce to post-bounce phase. So, well then, well here, let me just very quickly go through the results. So the common is that if the curvature propagation enters the bounds as a constant, then it always remains constant. But if there's a boost at the very beginning, then it can grow almost linearly in time. So this indeed can be this advantage can be used to depress the value of the tensor to scalar ratio. However, in the meanwhile, that might lead to the dangerous non-Gaussianity fluctuations. And this has been examined over here. And we find, for example, if we give for that single field model based on Hondesky, even R is smaller than 0.1 after the bound, then FNL can be extremely large. So that is far beyond the current observational limit. So then we made another conjecture. That is from the observational side, it looks like there is an observation no-go. And of course, even today, there are still a lot of discussions upon this conjecture if it is general enough. But at least from Hondesky and Hansen's models, and we realized for quantum fluctuations originated from the matrix-dominated contracting universe, then the upbound on the tensor to scalar ratio, which is sort of equivalent to the lower bound on the amplification of curvature perturbation during the bounce, and this can be equivalent to the lower bound on the primordial non-Gaussianity. So if the initial condition, initial vacuum is a quantum vacuum by letting an arbitrary CS, arbitrary value of CS, then actually this we realize there's no parameter space to satisfy both the observational upbound on tensor to scalar ratio and the FNL. And that might indicate a more realistic bounce model should go for the multi-field rather than the single field. So this is a conjecture from here. Chunshan?
Yes. Yes.
I remember my talk is 40 minutes or
45 minutes. So since you start 5 minutes late, I think you still have 3 minutes.
Three minutes, right?
Okay.
Yes.
Okay, so that might be fair for me. And here in the following, I just very quickly illustrate this no-go observation no-go indeed can be evaded by evolving more degree of freedoms, and actually that is also necessary because we expect for example the reheating of the whole universe, right? And so here it's one is from the basic picture of reheating, that is to require the energy restored originally from some primordial scalar field that can be transferred to excited particles at late time. And as a toy model, we consider this two-field model, m square phi square couples to a massless chi. So this chi can be called as an entropy field, which mimics the particles excited. So here, let me very quickly going through this one. So actually, we except for the particle productions, we also look at the perturbations seeded by this second scalar field, and we realize this scalar field, if it can be eventually converted to the curvature perturbation, and in the contracting during the bouncing phase, we when we write down the perturbation equation for this second field fluctuation, and then we realize this effective mass can become tectonic for a very short period, and then this factor actually can be applied to yield the amplification, so that it might be used to depress the tensor to scalar ratio if we can convert the entropy perturbation into the curvature perturbation after the bounce. So that actually looks like a curtain, a realization of the curtain for the matter bounce scenario. Okay, so I think it's really very timely, right? So today, in this talk, I introduce you a very brief review on nonsingular bounce cosmologies, and there's a very manifest advantage that it can avoid the big bang singularity. And in order to get a scale invariant path spectrum, typically we expect a phase of mass contraction. And also, we expect the anisotropic phase following this mass contraction, so that we can make sure this scenario can be classically stable against the anisotropy during when the universe remains contracting. And we showed that a single field model, which is Hondesky type, it suffers from the gradient instability during the bounce due to the theoretical no-go. And also for a single field model with a non-singular bounce that typically fails to meet the current observation, the combined observation constraints, both from the tensor to scalar ratio and from the primordial non-Gaussianity. So my understanding about toward the healthy version of non-singular bounce cosmology, then the above theoretical and observational challenges should be keep in mind when we play the game of model building. So yeah, thank you very much.
Thank you very much, Yifu. So let's thank the speaker. You can unmute your microphones to contribute.
Should we knock the table?
We have some time for questions. So if there are any questions, they are very welcome. There is another question from Michał, right? Michał?
Yes, so I have another question about the simple model with single scalar field, because it's so simple, it looks so nice. So I was wondering, what does the job? It's kinetic term, isn't it? Yeah, like I guess the potential only ensures that you have slow contraction, but the structure of the kinetic term makes you ghost free and all of the nice stuff, yeah? I just wonder if you could just keep adding different potentials to that, having different slow contracting solutions, keeping the structure of the kinetic term, and having a nice bounce after all.
Okay, that's a good question. Let me say, if you introduce more operators, and then I have to say the resolution to this system in analytic way will become more and more difficult. I mean, in general, from my experience. So,
You
for
mean
example,
operators on the kinetic
right,
side or the potential side?
Both true. For example, for this model, it's simple enough, but as I show you, this sound speed square become negative around the bounce point, and and then I wanted to show you that here over here that if you introduce a DHOST operator which encode these two terms, then you can cure this problem. But then the background evolution will become extremely unpredictable. What I mean the unpredictable means we still have the bounce, but then it's not it cannot be solved analytically.
So let me rephrase the question. My question is, let's say that you keep the structure of the kinetic term as you presented, you assume different background evolution. So this you have for free because you assume it, and then you reconstruct, you climb up to reconstruct the potential.
Right.
And so I guess that any potential would do, as long as because your problem is not within the potential, your problem is within the kinetic terms, and your kinetic term is constructed such as there is no problem.
Right. That's true.
Awesome.
Yeah.
That's fantastic, really.
Thank you.
So any other questions? Chun-san?
Oh yes, I have a comment. About this mass contracting phase. This contracting phase produce too large tensor to scalar ratio, and then anisotropic stress also grow as a to -6. My comment is if we assume that graviton has a mass, actually this is simple one assumption can solve both of two problems.
That's true. Yeah. Actually, Indeed, yeah. I didn't remember. I think you wrote a paper carrying out the gravitational mass can suppress the tensor to scale ratio, right?
Yeah, yes.
Yeah, I keep all this work in mind.
Ifo, I have a question concerning the gradient instability. The negative CS square implies that the type of your equation of motion changes type from hyperbolic to elliptic. Did you took into account that fact in the analysis of perturbations through the bounds? I mean, for that particular case, of course.
Indeed. So for the perturbation, okay, here, well, at the very last, I go through very quickly. So actually, this slide, the plot shows the different Fourier modes evolving through the bounds, and so we show that if our observational interest fall into the small k regime that goes to the infrared regime, then these perturbation modes remain almost unchanged. So they evolve through the bounds almost flatly. But with a larger and larger value for k, then you can see it growing up and then even, just blow up.
Yeah, but the thing is that they blow up because of the instability, actually. But the one way to cure instability is to treat the equations of motion properly. I mean, in the sense that your equation of motion, and in this case, the Mukano-Sasaki equation, is changing its type to the elliptic one. Therefore, I mean, the boundary condition is different, okay? Which is actually curing. If you take that into account and you basically solve a certain type of the Laplace equation in that case, with a certain boundary value implied by the pre-bounce contracting phase, then you can cure that effect. Just a comment. So this is something what we deal with in loop quantum cosmology in particular.
Right. That's good. Right. So actually, this is the argument that I buy for the loop quantum cosmology. Indeed, because how to say that? Yeah. This is I agree. Yeah.
Okay. So if there are no other comments, questions, let's thank Ifo once again.
Very good. Thank you.